Share the stage with well-known chemist Professor Altman. First of all, let me thank Professor Deepak for the kind invitation. It's my pleasure to be part of this prestigious program. My title is quite a bit unusual to what I do actually. So, in order to fit myself to this program, I had to reshape the theme of my talk. As you see, metal-free strategies to synthesize small organic molecule, including some fluorinated compounds. You can see eventually during my talk, we hardly make few compounds substituted somewhere with fluorine. Okay, I am not a fluorine chemist, I should admit. I am definitely nowhere comparison to Professor Altman. Otherwise, let me talk to you how we entered the metal-free scenario as of organic synthesis is concerned, and what kind of molecules that we synthesized, although we did not explore anything about the medicinal chemistry aspects of this. Probably some of you are more knowledgeable to guide me further, if at all something interesting that I am going to talk about. Let me start my talk by showcasing what we do at IISER Mohali nowadays. Earlier we used to have a different research area, but nowadays we have broadly two research areas to work on. One is the catalysis by phosphines. Apologies for this pointer, it does not necessarily show what I would like to point effectively, but go with me that we work on phosphine chemistry. Indeed, I'll start my discussion surrounding this phosphine chemistry, how we entered these cascade transformations promoted by sulforylates. This is a new research area, came out of nowhere actually. You will see how we entered this field, but our intention always is to create molecules for biological sake or for applications in materials chemistry. The background to the metal-free chemistry that came out of our lab is a simple transformation that we all know of. Any organic chemist must be able to realize what is this reaction, a Morita-Belli-Silman reaction, which is typically promoted by tertiary phosphines or amines. It involves a carbon-carbon bond formation leading to such densely functionalized molecules starting from the readily available compounds such as activated olefins and carbonyl compounds such as aldehydes or ketones. It's reported quite some time ago, almost I should say, as you see the reported publication early 1970s. What is interesting as of this particular reaction, indeed I should say how my teaching actually helped in coming up with this question. After teaching this Belli-Silman chemistry one day in a class while I was walking backwards, I realized that how and why always the chemistry is shown only with beta unsubstituted systems. What happens or what happened once you introduce substitution at the beta position to these activated olefins? That was a simple question I asked myself. Once I digged literature, I realized that this is a very common substrates. The one that I showed on the top equation, beta unsubstituted systems. Once you start introducing substitution, say let us say mono substituted one, very few examples, very few, and this is not general even now, these reactions are not even general. Once you have the beta position fully substituted, there are hardly any examples. Indeed, there were no efforts, especially in intermolecular sense, leading to such compounds. This is something that I realized. Okay, that means that once you have substitution introduced at the beta position, this reaction becomes more and more sluggish, and of course it reaches a stage that reaction does not work when it is beta disubstituted. Why? Of course, I try to convince myself probably this is not something worth thinking, because it is obviously because of steric reasons. Once you have beta disubstituents, that this incoming nucleophile cannot initiate the process leading to the enolate formation and subsequent transformation. Then I also found that the same reaction in intramolecular sense was also reported with beta unsubstituted variation. As you see here, such reactions leading to the cycloalkenes were also pursued with no substitution at the beta position. Of course, this is a beta mono substituted by virtue of being intramolecular. But otherwise, I did not find any cases where the beta position even in intramolecular sense were substituted here, leading to the respective products. So, with this background, we came up with this design. Actually, I could have spared some time to explain what is the origin of this particular substrate design, but because of the paucity of time, I will skip that part. But we came up with this design. If you see carefully, what the design effectively involves is the tethering of both the electrophiles. Of course, both are electrophiles from reaction point of view. For a phosphine to react, this is an electrophile. Once enolate forms, this is electrophile. So, these electrophiles situated ortho to each other, and they also assume what is so called synergism or mutual cooperativity. Okay. Once this is more electrophilic, for example, your first step where your phosphine or amine reacts, that can be faster, and once this is electrophilic, obviously that intramolecular aldol type reaction also will be faster, leading to the product. That was what we assumed for the driving forces behind this substrate design. Of course, eventually that is the product we realize, if at all the reaction is successful. And once it is intramolecular, unlike an intermolecular reaction, you all realize that it is entropy favored, unlike as I was saying, in intermolecular process. With this in mind, as you see, we initially went on with the monosubstituted systems. This is a typical methodology work. You may not really enjoy the other part that I am talking about, but once you have a beta monosubstituted system, the reaction works quite well, as you see, leading to variety of cyclopentane fused arenes and heteroarenes. And what especially encouraged us as part of this initial work was those highlighted in blue. Those are the substrates where where electron donating groups are substituted on some of the other component of the substrate, either it is in the arene backbone or on the enone component. Despite that, this reaction, as you see, works quite quick, no longer than 30 minutes that it requires, and of course highly stereo selectively, as you see the results displayed here. That gave us sufficient confidence, thinking that probably if at all the monosubstituted substrate giving you the product in such quick time, probably once you go forward to a beta disubstituted system, this reaction should give you the product indeed that can also establish a reaction leading to the first beta Belli-Silman reaction of beta disubstituted systems. Indeed, that is what happened. As you see here, we could amass a large number of large number of substrates where cyclopentane fused arenes, heteroarenes can be generated, but more importantly, as you see here, all are beta disubstituted systems. These are only first examples where Belli-Silman reaction was accomplished with beta disubstituents. You can also generate, as you see here, a quaternary carbon. You see last three cases are where quaternary carbon can be generated, tetrasubstituted carbon can be generated, provided you start with ketones. Okay. One obvious advantage with Belli-Silman chemistry is that it generates one stereo center, giving you the opportunity to pursue a chiral variation. Indeed, we spent quite a bit of time establishing the chiral variant. Ultimately, we were successful with this particular bifunctional catalyst where phosphine is situated here and a thiourea moiety on the other side. This reaction, for your information, provides the EE or NHA excess, as you see in these cases, only in HFIP solvent, hexafluoroisopropanol. Probably that fits me to this audience, that a fluorinated solvent, hexafluoroisopropanol, only gives you NHO induction in these cases. Okay. So, no other solvent. We spent almost 6 to 8 months exploring different combinations, because we did not want to publish this work without developing a chiral variant. We pursued so many combinations, so many catalyst solvent combinations. Eventually, you realize that only HFIP induces chirality into the product, and indeed this was the working model, although this model which is on the top right does not incorporate the role of HFIP, but eventually with the help of my colleague Dr. Balnarayan, we actually worked out a computational model which explains the role of HFIP in this transformation. If you see now what happens, this is the one that anchors substrate and the catalyst in a fashion that is shown here, forming this supramolecular assembly, and you can see that HFIP actually activates the substrate in this fashion that is shown here, and it eventually after the aldol cyclization transfers the proton, and the resulting alkoxide is actually responsible for the deprotonation, which is in the MBH context a rate determining step, and that promotes the elimination of phosphine and regeneration of the catalyst, and eventually the formation of the product. This also fits in, of course, this is a very short summary of the whole work just for the sake of chemists, but one can go through this paper and realize how detailed we worked, and that fits in the observed enantiomer selection in this particular process. Okay, having this as a background, we actually, I am just summarizing the work in the whole phosphine chemistry. We eventually went on to developing reductive aldol reaction promoted by phosphines, vinylogous aldol reaction. This is with activated alkenes on the left side. We also pursued intramolecular hydroalkylation chemistry using activated alkynes, as you see on the left, on the right, sorry, and then hydroacylation reactions leading to such products, and oxyamidation reaction, as you see. So a couple of other reactions we developed afterwards which are not captured here, but this is a summary of our contribution to phosphine chemistry. Okay, at this point we asked a simple question. This actually changed the course of the recent research in our lab. We asked a simple question based on the work that I just described, this Bailey-Silman chemistry. We asked a question, what can happen if I replace the double bond with a cyclopropane? Okay, one can understand that reactivity obviously won't be the same. While phosphines undergo a Michael addition followed by aldol cyclization leading to such products, which is effectively the Bailey-Silman products, the same won't be applicable in this case, because now phosphines have to be undergoing a homoconjugate addition, and that resultant enolate we are not very sure whether that they cyclize, or we are also at that point when we ask this question not sure what can be the fate of these substrates under the conditions envisioned. There is a simple logic, and the logic is that the double bonds or the cyclopropanes are considered double bond equivalents. That is the simple logic. Okay, most of the reactions exhibited by double bonds also exhibit as cyclopropanes. Okay, so that's the reason a comparison that is set between olefins and cyclopropanes. Okay, once we asked the question, we looked up what is known as of the transformations of cyclopropanes under Lewis basic conditions. As I was just telling you, phosphines are Lewis bases. What was known very interestingly is that the chemistry of donor acceptor cyclopropanes are the vinyl cyclopropanes, and the resulting chemistry originating from these deuterionic intermediates is very well captured. In fact, you can see the review that is here, and the representative paper cited at the bottom. This is very well known under Lewis basic setup. What is less known was the reactions promoted by Lewis bases and the gem deactivated cyclopropanes. Even it's so very less pursued. Even that much also is the contribution of Danishevsky way back in 1975, where he reported amine promoted ring opening cyclizations of cyclopropanes. But what is scarcely pursued was this particular case where monoactivated cyclopropanes and Lewis basic conditions leading to such deuterionic compounds and their subsequent transformations. Hardly known, and indeed we came across only one example in the literature, that is what is on the screen. Okay. In this case, if you see carefully, reported by Christoph and co-workers in 1987, phosphines react with the monoactivated cyclopropanes under the conditions shown here, form the products what are known as phosphonium salts. How this works? Phosphines undergo, as I was talking to you, homoconjugate addition, and the resulting enolate was quickly quenched by HBr, and that is what leads to what you see as phosphonium salts. What we thought, what about trapping, or is it possible to trap this intermediate? Okay. Rather than supplying HBr kind of a agent, what if I supply a reactant in the form of this XY, so that it potentially may undergo a 3+2 cycloaddition or a 3+2 equivalent leading to 5-membered carbocycles or heterocycles. Okay. So this is also the reason why we came up with the design that is shown in the last slide. So eventually, if you now combine the concept that is shown here and apply to the substrate that I was talking about. If you see this now, the cyclopropyl ketone having this aldehyde, which is effectively the same as what I showed in the last slide, under the influence of phosphine, which is effectively what is shown by Christoph and co-workers, you can see that this particular fragment is borrowed from here, and of course this is our design. Now it can undergo a cyclization as shown by these arrows, and they can deliver product shown there. Okay. This is when phosphines react from the R substituted carbon. Of course, it need not necessarily happen that way. The phosphines also can react or ring open the cyclopropanes from less substituted carbon, and that also can lead to similar products as you see in here. Of course, is a regioisomer to what you see earlier. Okay. But we are hopeful that because of precedence by Christoph and applying to our system, we are hopeful that we will get one or both of these products. Although you can understand that these are quite harsh conditions. I mean, this uses, as you see here, HBr, chloroform, 120 degrees seal tube conditions, quite harsh, but initially of course we never intended to go into that domain, but we wanted to see what can happen. Obviously it requires preparation of the desired compound. We wanted to prepare this compound so that we can execute the hypothesis that I have so far talked about. For this, what my student Uttam did was to take this compound, as you see here, the enone appended to that aldehyde, and he thought that the Korachekowski process would give him this one. Obviously, if at all you are familiar, I could have put up a Korachekowski reaction also here for the sake of students, but because time did not permit, I couldn't do that. But if at all you are familiar with the Korachekowski process, it need not necessarily give you cyclopropane, it can also give you an epoxide onto this carbonyl. And I asked him, why did you do this reaction? So he said, okay, fine, just to evaluate your proposal, I wanted to see, even if I get less yield of it, to evaluate the the hypothesis, even if I get less yield of it. But eventually what happened was that we isolated this compound. Okay. You can see that there is no correlation between what we expected versus what we isolated. The process we called as an interrupted Korachekowski reaction eventually, but how this works is this way. The sulfoxyonium ylate that is generated under these conditions undergoes 1,2 addition, and the alkoxide now exchanges proton, and the resultant ylate promotes intramolecular Michael addition, and the resultant enolate displaces sulfoxide DMSO, giving you the product as you see here. From nowhere, all of a sudden you see a 4 stereo center getting generated, and a compound that is otherwise difficult to access through traditional synthetic chemistry. And this was obtained in a 5:1 diastereomic ratio and excellent yield. Of course, this structure as such we could able to assign even before X-ray arrived, but that confirmed eventually the relative stereochemistry. This is the scope. This is something that any organic chemist does to satisfy the reviewers, right? You can see a variety of groups who are manipulated across the substrate and achieved complexity. This is one fluorinated compound we made, so which I will talk to you later. Yeah, here, yeah, that's the one. Thank you. Yeah. Because why I am pointing out is this spectrum I am going to show later. Anyway, this is what happened with enone appended to aldehyde. Obviously, as part of exploring the scope, we also checked the reactivity of enones appended to ketones under the same reaction conditions. You see that an entirely different product we achieved. It is now a spirocyclopropane. How this is obtained? Unlike a 1,2 addition that occurred in case of enone aldehydes, in this case, because now that these are ketones which are less reactive, probably that the sulfoxyonium ylate preferred a Michael addition, and of course a subsequent intramolecular aldol setting up this particular zwitterionic intermediate, and 1,3 proton shift leading to the enolate that is shown on the right. That enolate now promotes the elimination of DMSO, setting up the spirocyclopropane. Again, here also we have shown reasonable diversity through different example, only representative examples I am showing here. This concept we eventually applied in desymmetrization also, as you see here. What you saw was enone aldehydes, then enone ketones, and the other possibility is to have bis enones. Once you have bis enones, two types of bis enones possible, both are symmetric. This is the context of another publication and another work. Here also you get two different types of products. If you see these bis enones where the double bonds are internal, you get a cyclopropane fused indanes. On the other hand, once you have the other substrate, you now see a spirocyclopropane coming out. So, just to summarize up to here, this is what I showed you so far. You can see that different products are obtained with different substrates, effectively under the same condition. Reagent is the same, but different products are obtained. While we were searching, because we identified, obviously we realized that this is very interesting transformation. If at all we can expand the scope further, this would be more interesting to the community, was our intention. And while we were searching for few other electrophiles, we thought probably a pyridinium salt can be a good substitute. And however, we are not sure whether this reaction works under these conditions, because we are also not sure of the reactions between pyridinium salts and sulfoxonium ylides, because we do not want a reaction happening between the sulfoxonium ylides and pyridinium salts straight away. We want obviously the sulfoxonium interact with the enone first, and then the pyridinium should be reacting. But there was no precedence of a reaction between sulfoxonium salts and the pyridinium salts. But we went ahead, we prepared the compound as shown there, and subjected to the same reaction conditions, you can see what was obtained. We obtained these two compounds in 3:1 diastereomeric ratio, and both were isolated. Indeed, both were crystalline. We could readily establish the relative stereochemistry. What is more striking about it, it is not just about creating 3 stereocenters. 2 of them are spirocenters, all carbon quaternary spirocenters, vicinal spirocenters. Okay, in synthetic chemistry, usually you see several methods for the creation of spirocenters, but not vicinal spirocenters. This is quite rare example to that extent. Okay. Otherwise, this also represents an undescribed class of a scaffold. The scope was quite good, as you see here. I do not spend much time. Here also we have one substrate with a CF3 there. Otherwise, what is more interesting is the last one for me personally, because it now creates 3 stereocenters and 3 quaternary carbons contiguous. Okay, this is something that can be manipulated by introducing another substitution next to this R1. I mean to say, if at all you start with a beta disubstituted enone there, that translates to this blue carbon where you have now both R1, R2 substituted. You can now manipulate however you want. If it is a cyclic, that could have potentially been another spirocenter. But that is how we demonstrated the scope. You can see that all the products were obtained in, of course, good yields, moderate diastereo selection. Once we explored pyridinium salts, then we went on to obviously the relative of that is the quinolinium salts. Obviously, we expected similar products with quinolinium salts. You can see what happened there. Once we change to quinolinium salts, you can see entirely a different product. Okay, now you have to actually search for the cyclopropane. Where is it? It's such embedded deep in the product, as you see here, and all of a sudden you can see that you generated almost 6 to 7 stereocenters. It is even more if you want to include sulfur also as a stereocenter. But here also you can see the scope is quite broad, and of course here I am looking for, yeah, there is some fluorine compound here. Okay. And what is important in this case is, unlike pyridinium salts which we obtained in diastereomers, here all these products, despite creating up to 6 to 7 stereocenters, these compounds were isolated as single isomers. Okay, only of course this is an isomer because of the methyl group that we brought in from this alpha substitution that was responsible for the DR. Otherwise, everyone else are single isomers. Okay, this is a mechanism. I will be very quick. Sulfoxonium ylides in the case of pyridinium salts undergo 1,4 addition, and the enolate now undergo C4 cyclization, setting up the first spirocenter. Now the enol promoted displacement of DMSO sets up the second spirocenter and the third stereocenter. On the other hand, when we have the quinolinium salt, the mechanism diverges. As you see here, the enolate now exchanges proton with this sulfoxonium, forming this halide that now undergoes C4 cyclization, setting up this pyrocenter and forming this 7-membered ring. Now enamine promoted displacement of DMSO, leading to the creation of this cyclopropane, and DMSO interestingly re-enters the system in this fashion, and that is how you get the product as a single isomer. Okay, something I wanted to share here is about a folding strategy. What is a folding strategy? Okay, what you have seen so far is I am only changing the substrates. I am getting different products in different cases effectively under the same reaction condition, right. So, this is what is called as a folding strategy of diversity oriented synthesis. This is one variant of diversity oriented synthesis. What Schreiber defines this as a DOS strategy that converts a collection of substrates with pre-installed skeletal information into products having distinct molecular frameworks by employing common set of reaction conditions. If you read this definition, it exactly fits the observations that we made or the kind of results that I have so far shared with you. What I will do is I will share with you 2 more examples of this so called folding strategy that came out of our lab, and I will lead you to conclusion. This is one. If you see carefully the top substrate, the R1 is at the beta position, and you saw the product that is formed. Okay. Please pay attention to the substrate that is mentioned in the bottom equation. The R1 effectively is now at the alpha position, right. Rest are all same. You see the difference between the top and the bottom substrates. Okay. Only the difference is the R1, the position of R1. Of course, reaction conditions are same, but you see the product distribution. Okay. This is very different from whatever that was observed in the earlier case. Okay. This is the context of another work, and I will be very brief with this, the mechanism. Now sulfoxonium halide undergoes in this particular case Michael addition, setting up the zwitterionic species 1,5 proton transfer, forming this halide that is now responsible for the intramolecular aldol cyclization, and the resultant alkoxide promoted displacement of DMSO gives these 2 products in, of course, diastereomeric ratio. The ratio was not quite healthy, but good enough for a publication. That is enough for us, okay, at least at this point. You can see the scope of this work, multiple stereo centers. Otherwise, if at all you want to synthesize this kind of compounds using traditional synthetic chemistry, it definitely requires multi-step synthesis, but this is something except that you prepare the starting compound, one step everything is assembled in this fashion. You can even create or introduce 2 contiguous quaternary carbons provided you manipulate the substrate as you see here, and this is some synthetic elaborations taking this compound. You can take it to different types of derivatives, and needless to say that hydrofluorinones are very much prevalent in several bioactive molecules. Okay, this is another case. As I said, this is the second case. I will conclude as of the discussion surrounding the folding strategy. This work I just described, right. You saw that the quinolinium salts appended to this enone gave the substrate, right. This is the context of our earlier work. When we questioned what can happen with an enone in place of an enone, okay, for your information, the Korsakoffsky process works very well with enones or activated olefins leading to cyclopropanes, but that does not happen with activated alkynes. If at all you take activated alkyne and treat with Korsakoffsky reagent, you do not get a cyclopropane. Even if you get it, it is transient because it generates cyclopropenes or activated cyclopropenes not known in the literature. Okay. So, with that background, of course, we are aware of it, but reaction of sulfoxonium halide with activated alkynes will lead to gamma sulfoxonium enones. That is a different work altogether, which is known, but we question what can happen, and you see the product that we obtain out of this. Okay, completely unexpected. It took time for us to realize what happened here. Until the crystal structure arrived, we were unaware of the outcome of this. Okay, this is the scope of the work. You can see such intricate scaffolds you can create from nowhere, starting from a flat molecule. You have been listening to Professor Altman's lecture. As such, this institute is very well known for the drug discovery and related science. You know how skeletal diversity makes sense in terms of drug discovery. Okay, you can see the kind of skeletons that you create from flat molecules, such as what you see there. All of a sudden, you create sp3 rich systems, and this is the mechanism. Now, in this case, sulfoxylamide undergoes 1,4 addition, and the enolate or elinolate now undergoes C4 cyclization, setting up this pyrocenter. Enamine promoted SN2 prime type displacement of DMSO now sets up the cyclopropane, and what we believe is that intramolecular aldolene type cyclization then provides the product. Okay. So, further efforts, further designs are ongoing, and we actually are witnessing some great chemistry coming out of it. Okay, let me come back to this question. All of you remember this one now? We deviated to sulfoxyonium chemistry. I showed you how we entered the sulfoxyonium chemistry accidentally. But coming back to our original question, the cyclopropyl ketoaldehydes, we now prepared by protecting this aldehyde. Earlier you remember we did not protect the aldehyde, and you saw what happened. Now we protected the aldehyde and prepared purposefully this cyclopropyl ketoaldehyde subjected to phosphine and DMSO heating. We expected this product, you remember this hypothesis, we expected this, but we actually got this indinone. What was more surprising to us was this: it did not actually require phosphine. Out of some control experiments when we did, we realized that DMSO alone can facilitate this transformation. More surprising thing is that it's not limited to this substrate. You can see, I am only summarizing due to the lack of time. You can see that with aldehydes, when the Fg, what I am trying to say is, when this functional group is aldehyde, this is the product you obtain, that is what is shown there. When this functional group is a ketone, you get alpha styryl indinones. When this functional group is in enone, you get to these fluorinones. Okay? That is the scope of this work, but the question remains, how about phosphines promoting ring opening transformations of cyclopropyl ketones? Can this be achieved? This is, again, I am summarizing in one slide. This could be achieved in this fashion. Against aldehyde that I shown, if at all you have this enone in place of what I showed as in the earlier case aldehyde, you actually can access tetrahydrofluorinones. This actually represents the first, at least to our knowledge, first Lewis base promoted ring opening transformations of activated cyclopropanes. Okay? Lewis acid promoted transformations of cyclopropanes are quite well known, widely known, not just Lewis acid, even bronzed acid, but this is Lewis base promoted, that is in the form of a phosphine. Although this is an unintended result, because we did not plan this obviously, we wanted to see what happens, but we got after the ring opening transformation of cyclopropane, proton transfer gave this ylide, intramolecular Wittig reaction gave this tetrahydrofluorinones. Okay? That is what it is. This is very briefly. Again, I am not taking much of your time, just to showcase the scope, and much more was done, of course, in the context of that publication. But this is to conclude what I am talking about. We asked this question, all of you remember, we asked this question, what can happen with monoactivated cyclopropanes appended to aldehydes? Can we get this product? And you saw this story surrounding this particular question. And achieved, this is what we achieved so far. What we achieved, just as I shown, a cyclopropyl ketone appended to enone giving tetrahydrofluorinones. Okay? This is the latest work unpublished, still in progress. We indeed can obtain cyclopropyl ketoaldehydes giving you this product, which is what was originally hypothesized, but a slight variation in the design. If you see here, now this is no longer a monoactivated cyclopropane, is a geminally diactivated cyclopropane. So, so far that is what I mentioned, not achieved so far is the comment. With monoactivated cyclopropane aldehydes, we could not yet transform them to the kind of products that we were expecting, but so far we could achieve to the products that are here. Okay? Provided you have an additional withdrawing group, otherwise additional activator comprising to geminally deactivated cyclopropanes. Okay. So, this is slide I wanted to impress Professor Altman. I introduced this slide. I know Professor Altman worked on decarboxylative alylation reactions using palladium. Of course, he is a versatile chemist. He has worked in other fields also, but this is something, a closed chapter in our lab. Just to summarize, we developed palladium catalyzed intramolecular aldolene cyclization reactions leading to these cyclopentadienes, and we also developed Nazaro type cyclization leading to such structures. We made some small natural products within that context, and of course this is one natural product. Of course, these are materially interesting. This is benzonylation reactions we developed, and using the geminally disubstituted acetates, we could actually achieve formation of chromines and small natural products in that context. Also, we almost stopped working in this field. One last work is pending just to culminate our studies in this field, but otherwise very brief. I will take only 5 more minutes, okay, just to talk about some fluorine chemistry. It's a very important nucleus in NMR spectroscopy because of its, as I mentioned, receptivity and large chemical shift dispersion, even much better than proton NMR, for example, or proton or 1H NMR. Okay. The abundance is 100% F19 NMR, 100%. It has a nucleus spin of half, which makes it responsible for its coupling with other nuclei. Right? All of you must be probably by now aware of this. And the kind of spectra I am going to show in the next few slides are recorded in a 400 megahertz NMR, indicating to you that the field strength is 376. Okay. This is something based on certain calculation which you can arrive at this number based on the abundance and the field strength. Okay. This is one compound, and just as we record nowadays NMR decoupled. For example, C13 NMR, they are primarily decoupled from protons, and to simplify. Okay. What you can see in this molecule I described already. Okay. What is important here, of course, this is also a decoupled spectrum, decoupled from, proton decoupled F19 NMR spectrum. Okay. If you see here, this particular doublet like, these look like two singlets, but this is actually a doublet. What is this doublet responsible? This carbon, now this fluorine or F19 here is responsible for splitting this, and this is the doublet that is responsible for that. And whatever the J value that you calculate in proton NMR, you also have to measure here, but you have to multiply by the 376 factor, right, so that you arrive at the J value. And you can also see this is also one. Fluorine is so interesting. I don't need to tell in front of Professor Altman. I should not tell more of fluorine, but fluorine is so interesting. It literally can affect everything that it is connected, especially in aromatic ring. It can literally influence all the 6 carbons of the aromatic ring. In some cases, you will see even it goes beyond that also. Okay, that depends on substrate to substrate, and you will see that all 6 are here. Actually, 1, 2, there is 3, 4 here. Here 4, 3, 4, 5, 6. Okay, followed, right? 1, 2, 3, 4, 5, 6. Okay, these are all, of course, I am not showing you the zoomed portion of it, but these are all because of the CF coupling. Okay, this is the respective F19 NMR as you see here. Just as proton NMR, in proton NMR we take proton or 1H as the reference. In this F19 as the reference we take, and you can see that this is effectively representing this fluorine, right. You can see the chemical shift -100. -100 is nothing in fluorine NMR. It can go up to 800 also, depending on the scenario. Okay. This one, and this is another molecule I already described. Here also you can see that this fluorine has created the doublet here. You can see the kind of course these are not 2 peaks. Okay, you need to be careful in interpreting your NMR. When you are writing the data, you should not write them as 2 peaks, okay, especially when you have fluorine around. Yeah, and you have 2. This is 1, 2, 3, 4 here, 5, 6. Okay, 6 carbons coming from the aromatic. Okay, and indeed, what we saw a slight influence on this carbon is effectively this carbon, the OH connected carbon, slightly influenced by of the range of 1 hertz. Okay. So, that much influence, it has influenced up to the benzylic carbon. Please correct me if I am wrong, but we believe that it is because of the fluorine coupling. And then this is the respective F19 NMR, and this compound already showed you so far whatever are shown, two structures are with CF bond. Now it is CF3. Okay. CF3, because this is see, for example, if you record CH3, if you do not record decoupled, okay, CH3 also will appear as a quartet in a coupled, proton coupled C13 NMR. I hope you are following what I mean. If only you will see that CH3 as a singlet only when you decouple the proton, right. So, here now CF3, okay, CF3 now will appear as a quartet, okay, as a quartet in NMR which is embedded somewhere here. Okay. I again I could not identify through the zoomed variant. But otherwise the fluorine also influences other carbons coming out of this particular presence. Okay. Here you can see that while we saw F19 of CF at -100, a CF3 now I mean fluorines on CF3 appear at -62 in this particular context. Okay. Similarly, we can talk about several other fluorine containing compounds, but I thought I should talk as less as possible as of fluorine chemistry, especially in its presence. So, I thought I should conclude there. I thank my students for their contributions and funding agencies for their support over the period. Thank you very much. I hope I was on time. Sorry. Okay, it's 4:05.
Any questions? Yeah.
Sir, you have shown on slide there is a atom group phosphine base on the less substituted carbon of cyclopropyl. In hypothesis.
Right.
So is that possible it can attach to that carbon because the electronegativity difference by electron withdrawing group and electron donating group is more, but it can be attached to less substituted carbon.
Yeah. No, that was.
Any evidence or
No, there is no evidence obviously. So it was only an expectation. See, once you have a cyclopropane, so there is a possibility. For example, I have. Okay, if I have cyclopropane like this, you see that this bond is activated by the presence of this ketone. This bond also equally activated by this ketone. That's why when we hypothesized the nucleophile attacks from this way or this way. You got right? That's the origin of that. Other than that, we have no idea, because phosphine promoted ring opening transformations as cyclopropanes, perhaps, at least I should say, first we reported.
if it is like donor acceptor?
That is different. That is very well known. Donor acceptors, yeah, in fact, I told you about that, right? So, donor acceptor systems are very well known. Okay, but we are see, if I had to deal with donor acceptor systems, we would not have entered this field, because that is so well explored. Okay, as you see here, these two are quite well explored. As I was mentioning, indeed there are reviews on that topic also. These are also reasonably well known, not as much explored as this topic. This is something, as I was telling, in this context only one report was known, that is this monoactivated cyclopropane ring opening transformation. This is the only report to our knowledge.
Hypothesis you have shown in one slide.
Yeah.
There is that phosphine attached to the less substituted carbon.
This one.
Red one.
Okay.
Is that possible?
That's what I am showing here. So probably you are confused because there is no R there. But same. See, if I put R now, you will see. So that's what it is. Okay, because these two bonds are same for a cyclopropane, same for the ketone. Activation can be similar in both, but one bond may be more activated than the other by the presence of this R group, nature of that R group. Yeah. Yeah, you're right. If it is withdrawing, then probably this bond is more prone to cleave. Yeah, that's what it is. Yeah. Yes, please.
In your slides, there were so many stable sectors.
Right.
And usually we don't feel, means we don't have that much exposure within the time in analytical perspective
Uh-huh.
to analyze the stereo center, right?
Right.
So how did you analyze, apart from X-ray crystallography, which analytical techniques you utilize to identify this stereo syntheticity?
Mm-hmm. Yeah, this is the NMR. Without NMR, the simple answer NMR. Okay. Without NMR, obviously, if you don't have X-ray structure, obviously, my supervisor is to say, ideally, organic chemists should not rely on X-ray. Before that, you are supposed to, if you are a good organic chemist, you are supposed to deduce the structure based on NMR data. That's what he used to suggest us. But what I'm trying to say is, all the stereochemistries were assigned based on NMR data. Okay. Once you, for example, you have SYN stereo centers, the respective protons, you can identify the coupling constant or the J value that you call. Based on that, you can assume, or you can come to an estimation of whether they are syn or anti. Okay. So these are like the protons in see, these protons, right? So the cis and trans protons we talk about, right? All of you know that when you talk of J value, we all know that the trans has higher J value, cis has lower J value. Based on that, you can say. But once you are in a sp3 system, these things don't hold. Okay. Once you are in sp3 system, what I mean is, if at all you have something like this, for example, these are antiprotons, right? And the antiprotons, the J value is actually is reverse to what you have here. J value will be less here in the sp3 scenario versus the syn. Okay. So these things you have to be realizing before you are handling such compounds, and added to that the other data such as X-ray or whatsoever that helps you. And as such, you may be having some prior idea of your mechanism, right? When you are doing a reaction, for you probably it is new, but for me, I have some experience with this, so I know what can be the progress of the mechanism. Based on that also, I can have an idea what can be a preferred stereoisomer or whatever that is possible or not possible.
That's why I think it's very important that looking at your spending time on your data.
Yeah.
So nowadays, what happening that you just spend, if for example, if you spend 600 rupees manually, you get just extra, and you actually once you get one NMR, you just spend half hour, 1 hour on that. So I remember Dr. Haridwar, he is now still my supervisor. He used to have a like a box with like several pencils, eraser, sharpener, and then as soon as extra comes, he's so happy. He will take and sit, and then he'll keep on drawing all the possible structures, write down all the structures. So 1D NMR, and then you can go to 2D NMR and see
Yeah,
whether
yeah, 2D. Of course, NMR I said, within NMR you have 1D, 2D NMR. 2D NMR is another very helpful technique. Yes.
Yeah, many times, many compounds he said that they will struggle until they get crystal center. So it is not possible that you just set up the crystallization and you
Yeah,
get next day.
yeah.
Sometimes it may take 6 months
Yeah, yeah,
to
true,
get a
true, true.
crystal
Yeah,
structure,
yeah,
and
yeah.
we cannot
Organic
we
chemists.
cannot sleep if you have a structure data and you don't know. Sorry, you have data and you don't know the structure. So it is always goes around in your when you sleep also. So one
True,
day
true.
you can have a dream and the molecule is in front of you.
Yeah, yeah, true. I agree. Yeah. Because especially
Anything else?
organic compounds usually are not very much crystalline, usually, unless you are blessed.
So I think that is wonderful, and so thanks to Dr. Ramshastri for
Yeah.
including some data also.
Thank you.
Like